So the best way to understand the limit definition of the derivative is to actually see it through the lens of our normal slope equation. So let's take this function y is equals negative x cubed plus 6x minus 2x plus 2, and let's actually just find the good old algebraic slope between these two green dots and purple dot. As you recall, our slope equation is just y2 minus y1 all divided by x2 minus x1. In this particular problem, our coordinates for x2, y2 is 1.8 and negative 0.52. So then for y2, I'm going to put on the top here, negative 0.592. And then for x2, it's going to be 1.8. And I'm going to subtract from both of these the y1 and x1. In our case, y1 is negative 2. And then our x1 is just 1. If you subtract this out, you'll get a numerator equal to 1.4 and a denominator equal to 0.8. Solve this out, you will get a slope of 1.76. And visually, this slope is just the little direct line slope between the green dot and purple dot. And then we call this direct slope line slope of the secant line. So our little orange line right there, the slope of which has is 1.76. So now let's translate what we found using good old algebra slope equation into this limit definition of derivative. The easiest place to start is the denominator. In our original slope equation, we have x2 minus x1 as a denominator. For the limit definition derivative, we're going to take the difference between x2 and x1, or this horizontal distance here between this dot, that horizontal distance right there, instead of calling it x2 minus x1, we're just going to give it to the variable h. So in this case, looking at our limit difference formula, we know that our h value, we solved it earlier, which is 1.8 minus 1, or x2 minus x1. So our h value here is just equal to 0.8. Our f of x value, we know that f of x is really the same thing as just a y. So these x's, because we're just using the first x, this is really x1 on this equation. So f of x1 is nothing more than our y1. So this right here, this part right there, that's just y1. So going to our equation, we know that our y1 is again equal to negative 2. The trickiest part of this conversion equation is that f of x1 plus h. What that is saying, we know that this is supposed to be y2. So this section here, that's y2. But we're going to express y2 as a function of x. So the first logical step is this is supposed to be f of x2, but we're not going to use the x2. We're looking at the equation down here. So we re-express x2 as a function of h. So looking at the distance here, we have x1 down here. If we were to add to that this h distance to the x value, the h horizontal distance, that is actually how you're going to get to x2. So here in the substitution then, instead of f of x2, this is going to be rewritten as x1 plus h. And then, of course, even though we have this expensive f of x1 plus h, all that really saying is tracing all the way back is just y2. So in this case, our y2 value here is just negative 0.592. Whether we use the original algebraic slope equation of y2 minus y1 equals x2 minus x1, giving us a slope of 1.76. Using the limit definition, we still also get the same 1.76. We're just using different symbol notation. The reason this is important is because our algebraic slope equation just finds us the slope between the green dot and the purple dot. But the point of the limit definition is that we're going to redo this process and we're going to choose another dot even closer than 1.8. So for example, let's redo this whole process. For this case, we're going to choose, imagine we have an x3 here. So we're going to make a dot even closer to this. And let's arbitrarily choose an x3 value of say 1.4. So here, our x3 value is 1.4. And then given our coordinates here, will be 1.4, and a y value, plug it into this original y equals minus x cubed plus 6x minus 9x plus 2, and we plug in 1.4 into that equation, we would get a y value of negative 1.584. Now we repeat this whole entire process now. So instead of y2 minus y1 and x2 minus x1, the 2's now become 3. So it becomes y3, x3 minus x1. So we repeat the entire process. So y3 in this case is negative 1.584 minus, again, our same y from before, which is negative 2, divided by, we have our x3 in this case, we found it to be 1.4, and then we're going to subtract it from our x1, which in this case is just 1. Calculating the numerator, we will get a 0.416. And the denominator, we just get 0.4. And dividing that out, we will get a slope of 1.04. Notice that the slope has decreased to 1.04 from the previous x2 value, which makes sense because if you look at these two secant lines, the first one was between the green and the orange, and then the next one now is between the green and the red, and you see it's flatter. Now, if we take this logical progression completely through, we will keep on choosing dots with an x value closer and closer to x1. And if you choose values closer and closer to x1, that's what the limit definition derivative is saying. This h going to 0, you're trying to choose the difference between the two dots where the horizontal distance get closer and closer to 0, where it eventually ends up at 0. And if you end up at 0, you will get the actual instantaneous slope at the green dot. Little definition of derivative, it just allows us to find the instantaneous slope at that green dot using the logic of just taking slopes of dots getting closer and closer to the original green dot, or minimizing the h distance, making the limit going h to 0. So in summary, you can see that the limit definition of derivative just tells you to do the slope equation over and over again, because the limit going h to 0 part is telling you to choose dots where the second x value gets closer and closer to the original x value, making that difference h making 0. And then the definition of derivative is no more than the slope equation, just changed up to different variable. Here is a simulation so you can see for yourself how the slope is constantly changing. So just like in our sketch example, in this case, we'll start at the x1 and y1 will start at the same 1, negative 2, but in this case, we'll start at a x2, y2 at 2, 0. And you see on the right over on the corner, you see the slope here, calculating this, it's just a nice slope of 2. And then going to choosing another dot closer to our green dot, which is the example we just worked through initially, we see again that this slope here is 1.76 when our x2 is 1.8, or 0.8 closer than before. And then choosing the next one here, our h value is 0.6 because the x values are 0.6 away from each other, and you see the slope is now 1.4. And let's now just look at the slope trends as we get closer and closer. So now it's at 1.4, now it's 1.25 when x2 is 1.5, now is 1.04. If we skip it a couple of times, we've got 1.81, 1.56, 1.427, so on and so forth. And as you see visually, the slope is getting flatter and flatter. So by logical deduction, if you were to go as infinitesimally close to the green dot as you can, the slope would decrease to 0, which is represented by a horizontal line.